Welcome to the session that replaces the lecture from Thursday, August 5. We had technical difficulties. If you were not in the classroom, you were probably not able to see what was happening, but the Zoom application was repeatedly crashing and just became impossible to use it. So I'm sorry about that. I did contact tech support. They have assured me that it is now working, and I have my own equipment also, which I'll be bringing with me to class next time. So in case there is another failure with the classroom equipment, I'll be able to switch over to mine, and then we'll keep the class going. For this lesson, we want to progress on to working with discontinuous functions with a Laplace transform. Now, what I plan to do here in this lesson is to break these videos up into some smaller segments. So I'll try to label those from Blackboard, so you'll be able to see which ones you need to watch, and if you need to go back, you'll be able to zoom in a little bit closer than just to pick your way through the entire lecture. That's an option I do not have when we're doing a Zoom session. That it's just the whole thing or nothing. So for discontinuous functions, it turns out that we're going to be focusing on two different functions. The first one is known as the unit step function, and we define that in this way. Ut minus a, and in practice that a is a number, so it would be like t minus 2. The unit step function is equal to 0 if t is less than a, and 1 if t is more than a. So this is a very, very simple function. Along the t-axis, you have a point A, and let's say that 0 is about here, and then what happens is you come right up to A, and at A there's a jump, and then it's equal to 1. And so it would be natural to ask the question, well, why would you do that? Well, the answer is we use that essentially like a switch. If you think of it, the switch is off here and the switch is on here. So we use this to turn other functions on and off, and so we take other functions and multiply them by ut minus a. This minus a, that's a right shift. If you just had u of t, so that a were 0, it would do that jump at the origin. But by shifting it, by adding or subtracting a number a, then you can shift it left or right and make that turn on and turn off wherever you wish. The unit step function is then typically used as a factor in more complicated expressions. For instance, with this expression here, I've got ut minus pi over 2 times the sine of t pi over 2. Now, t minus pi over 2, rather than just having t there, that means we've shifted the sine function to the right by pi over 2 units. And this means we turn it on at pi over 2 units, and it's off until you get there. So if you were to look at the graph, you would actually see something like this. The function is just hovering along at 0 until you get to this point, which is pi over 2, and then it turns on and it continues to run. Now you could also use the unit step function to turn a function like this back off, and I'll be explaining that in more detail as we get into the lesson. The most important use of this, actually, there are cases where you want to build up a function like this that turns a piece on, turns another piece off, and that's certainly a valid use of the unit step function. But probably the most important use comes from this equation right here, that if you take the Laplace transform of ut minus a times f at t minus a, for instance, that f might be the sine function we've got here, and the a could be pi over 2. If you transform that under the Laplace transform, you just get e to the minus as times whatever you would get if you just transformed f of t. Now, this is not the version that is most commonly used. The most commonly used one is to state it in reverse. The inverse transform of e to the minus as f at s is ut minus a f at t minus a. And this one comes up when we're solving differential equations because there's another function that we want to use, and we'll transition to that right now, and that is the Dirac delta function. The Dirac delta function, and by the way, I'm still on the topic of why we want that unit step function. It's because we want to use this. And why do we want to use this? Well, this function is defined, again, it's a discontinuous function, only this one is really pretty weird. If you're thinking of classical functions, it really just does not fit the pattern at all. There is no classical function that has this behavior, but there is mathematical theory that will justify this, and these kinds of functions are called distributions, and it has these properties. First of all, this delta t minus a, the Dirac delta function, is equal to 0 everywhere except a single point a. At that point, we think of this as being infinitely tall. And it has this property: if you integrate over the point A, so this means integrating a little bit to the left of A and a little bit to the right of A, you're always going to get 1. So it's like the area under the curve is 1, but it's concentrated at a single point. And of course, somebody might think, well, how on earth could that happen? Well, it can't happen with a classically defined function, but we think of it as being some kind of a limit of this kind of a function here. Suppose we had a function that's 0 everywhere except on the interval from a to a plus k, and k is getting close to 0 from the right. So it's a positive number, but it's getting very close to 0. Then if we made the height of this function 1 over k, and we make the width of this interval k, then k times 1 over k is 1, right? So if you integrated this thing from 0 to the infinity, it would be exactly the same as integrating it from a to a plus k, because the only place it's non-zero is right there, and every time you'd get 1. Well, now just imagine that interval shrinks down and gets really, really, really small. Well, you start getting things that are acting kind of like this, right? All of the area is concentrated pretty much at a single point, a plus epsilon, and it's 0 everywhere else. But when you integrate it, you get 1. So that's what we're thinking of when we are thinking of the Dirac delta function. Now, why are we interested in this? Well, because in a lot of physical systems, you can have behaviors that kind of act this way. Suppose you had a mass spring system in static equilibrium. So the mass is hanging from a spring, may or may not be damping in the system, and you come along and just wrap that weight from the bottom with a hammer. Well, what you have is in a very short period of time, you've imparted a finite amount of energy into the system. So we usually use this function, at least for this class. The only thing we use it for is an input to a differential equation, and it would mean something like that. Or you can have something like this where you have like an arcing behavior in a circuit, right? Over a very, very short period of time, you have a significant amount of energy can be imparted into the circuit, and how is it going to respond? Now, there is a formula for the Laplace transform of the Dirac delta function, and that's that e to the minus as. And that explains why we care about that first shifting theorem that I had up here just a moment ago, because this e to the as will then end up on the right-hand side of an equation times the transform of something else, and we'd like to be able to take the inverse transform to to solve the equation, and we end up using this. Now that's all very vague and abstract, but we'll make it very concrete here in just a little bit, because next segment I'm going to review a little bit of what we've done with Laplace transforms, and then we're going to start computing transforms, inverse transforms, and solving equations.